let's start with our pieces of advice, which is, of course, you've seen this before, and it hasn't changed because this is how you do well. The first thing is you got to do problems. And there's the problems today, but there's also problems from old final exam reviews. We've been doing final exam reviews now for a couple of semesters. They're not going to be the same problems, and some of them are not relevant because they are not going to cover the same material that we covered. But a lot of them are relevant, and the more that you see, you'll see there's a wide variety of problems. And once you see the wide variety, you'll start to see, okay, there's many things that you can do. And it's really important to understand ideas, not just be like, okay, here's a problem type. As long as they give me the problem phrased in the exact same way, but they just change a number here, I'm okay. We want you to get beyond that. We want you to say, okay, I understand the ideas, and they can present a problem to me in a variety of ways, and I'll be fine. I can do that. And the way you get to that point is you do problems. And of course, take care of your health. This is the final exam season coming up. That's very stressful, and both physically and mentally. So give yourself plenty of time to study for the final, and while you're studying, take breaks. Go out and yell outside if you need to let off some steam, whatever you need to help you get through that period. So let's begin. Okay. So number one, you are conducting an experiment, and to help minimize the risk of the process, you need to find the minimum average rate of change for the interval 0 less than or equal to x less than or equal to a, where a is greater than 0. So we're looking for really what's the minimum average rate of change for some choice of a. What's our function? It's the function 2x to the fourth minus 3x cubed minus 36x squared plus 42x plus 250. Now there's a couple of key words here. And one of the things we want to do is get to the point where we look at a problem and we say, okay, I can pick up what it's asking. So the first key word we're going to cue off of is minimum. So when something is asking for a minimum, that's asking for optimization. We're trying to find the largest or the smallest of some expression. But there's another key thing here, which is this phrase average rate of change. Now, when we see the word average rate of change, that triggers something very particular. So the average rate of change, so if I'm talking about the function f of x for some interval, say between a and b, then the average rate of change formula, I'll abbreviate that AROC, that's equal to f of b minus f of a over b minus a. So whenever we see the word average rate of change, that's what we think of. Now, what are we after? Well, we want to look at the average rate of change from 0 up to a. So let's apply the formula. In here, well, we'll change the name slightly, but that's all right. We look at f of a minus f of 0 over a minus 0. So what's that? Well, so plug f of a in. That's 2a to the fourth minus 3a cubed minus 36a squared plus 42a plus 250. That's f of a. Subtract. Plug in 0. Well, that's just the 250. Everything else goes away. All that over a. All right, so that's our average rate of change. Now we can clean this up. The 250s cancel, so that's good news. And then we can divide through by a. So what do we end up with? We have the function 2a cubed minus 3a squared minus 36a plus 42. So our goal is we want to minimize this function. And so in particular, we were thinking like, well, how do we minimize it? The only thing we can choose is a. All right, so now we've done the hard part of an optimization problem. We have solved for a function. We've got it down to a function of just one thing that we vary, a function of one variable. And once we have that, we say, okay, what's next? Well, let's for a second, we'll call this, we need to give this a name, we'll call this g of a. So g of a is the average rate of change between 0 and a. So we're trying to optimize that. So now we take our derivative, g prime of a. So that would be 6a squared minus 6a minus 36. All right. Well, what does that turn out to be? Well, we can factor the 6 out. A squared minus a minus 6. And if we're lucky, if we've lived a good life, then things will factor. Well, I think we've lived a good life. A minus 3, a plus 2. And we get two candidates. Well, 3 and negative 2. Well, we can knock out negative 2 because we're told a is positive. Can't be that. So we really only have one candidate. So we can conclude that it seems to be the case that this should be a equals 3 is where the min occurs. Now, you might say, hold on, how do we know that's a min? Maybe it's a max. You've done something terrible. That's actually a good point. So we should be ready to justify. So let's do a quick justify. So we have our g prime of a. It exists for all numbers. And really, what happens? Something can happen at 3 and at negative 2. If you plug in 0, or it doesn't have to be 0, you can plug in 1 if you're nervous about 0. You can say, well, look, okay, let's plug in 1. That way, you don't have to be nervous about 0 over 0 here. Plug in 1. You'll get 6 minus 36. So that tells you that g prime is negative. Now plug in 5 or 100, maybe a million. 6 times a million squared minus 6 times a million minus 36. Yeah, definitely positive. Going up. So I go down, then I go up. And so I can conclude a equals 3 is a min. Good. Good. So we definitely know when it occurs. But we've got to be careful here because what is it we're trying to find? We're trying to find the minimum average rate of change. This tells us when we get a minimum. So our answer is going to be plug 3 in. So we plug 3 into here. So now we get 2 times 3 cubed minus 3 times 3 squared minus 36 times 3 plus 42. Now, this is probably more than we really want to deal with. That's okay. You know, if this is too much, we just say, look, that's perfectly fine, valid answer. Of course, we can clean it up a little bit. 3 cubed is 27 times by 2 makes 54. 3 times 3 squared, well, that's 3 cubed, so that's 27. 36 times 3, well, that's 108. It's like 90 and 18. And then, of course, 42. It's the answer to life, the universe, and everything. Also, the question to what is 42 worth? It's worth 42. So we get 96, 54 plus 42. And then we're going to subtract 135. Yes? Because if you take 27 and 108, that would be 135. And, well, what does this turn out to be? And, good question. And the answer is a number. All right. We've come this far. Let's go all the way. So 96 versus 135. Well, suppose it was 135 minus 96. Well, that's not so bad. It only takes me 4 to go from 96 to 100, and then 35 more to get up to 135. So that would get me up to 39. Of course, if it was the other way around, so if I flip, that's negative 39. And therefore, that is our minimum average rate of change. All right. Well, now we know. Good. So, next one. Number 2. Find the tangent line to the function f of x, which is the integral from 2 up to sine of 3x, the square root of 4 minus t squared, at x equals 2 pi. So here, again, there's a couple of things to note. First off, the word tangent line. You are probably going to see multiple problems on this final that involve a tangent line. Because tangent lines are really important. They're sort of the bread and butter of calculus. That's what we're saying we're trying to approximate a function. So be prepared to handle tangent lines. There's something else that you see here going on, which is that you see an integral with a function up in the bounds. So when you see an integral with a function in the bounds, that's a signal to you that this problem involves the fundamental theorem of calculus. So if you see that and you think, okay, I see an integral, I see a function of bounds, FTC. Now, what do we mean by fundamental theorem of calculus? When we say fundamental theorem of calculus, we almost always mean this variation. Integral from a constant up to x of some function f of t dt is f of x. Of course, there's other variations, and we'll probably use the following. Instead of going from c up to x, maybe we'll go to c up to g of x of f of t dt. Because that's really what we have here, is we have sine of 3x. And when you do this, what you're doing is you're adding in the chain rule with the fundamental theorem. That gives you f of g of x times g prime of x. Because remember, the chain rule says take the derivative of the outside, but now you plug the inside in. G of x is the inside function, and so you plug g of x into f times by the derivative of g. So by looking at the problem, we already pulled out that we need to focus on these pieces. Now, when you're looking for a tangent line, that always says, okay, I need two pieces of information, the value of the function at the point, and our point is 2 pi, and the value of the derivative of the function at that point. So that's f prime of 2 pi. So let's work through both of these. So we'll start with, say, f of 2 pi. So how do you figure that out? Well, the answer is you plug it in. So f of 2 pi is the integral 2 to sine of 3 times 2 pi, which is 6 pi, times the square root 4 minus t squared dt. Well, sine of 6 pi is 0. So this becomes the integral from 2 up to 0 of the square root of 4 minus t squared dt. The bounds, they're in sort of the wrong order. We like to go from low number to high number, so let's flip the bounds. And if you flip the bounds, you're essentially changing the orientation, so you need to put a negative. So negative integral 0 to t squared of 4 minus t squared dt. Now this is an integral that we sort of have two things that we've been telling everyone. First off, you can't find the antiderivative. But second off, just because you can't find the antiderivative doesn't mean you can't do the definite integral. Because if you see something of the form square root of a number squared minus a variable squared, say u squared du, something like that. I don't need a du. So I don't know what this number could vary. And what you really are dealing with is a circle. So here, we should recognize that this is a circle. It's a circle of radius 2, because that's 2 squared. And we're going from 0 to 2. So we say, okay, so what are we after? Well, this can be interpreted as the area of 1/4 of the unit circle of radius 2. So normally a circle of radius 2, the whole circle would have area pi r squared, which is 4 pi. 1/4 of that would be pi. So this integral turns out to be negative pi. The negative because of the negative, and this because we can interpret it as an area. So negative pi. So that's half of our tangent line. So for the other half, that's where we're pulling out the fundamental theorem, because we need to take the derivative. So I need to take the derivative of this expression, and now we have that right there ready to go. So before we write down f prime of 2 pi, we'll write down what is f prime of x. And the answer is that f prime of x is going to be, I take the square root of 4 minus sine of 3x squared times cosine of 3x times 3. So what just happened here? Well, what happened is that we plugged in the sine of 3x everywhere that we saw a t. So that's how we got the square root of 4 minus sine of 3x squared. And then we times it by the derivative of sine of 3x. So we plug in 2 pi. So f prime of 2 pi, well, that's the square root of 4 minus sine of 6 pi squared times cosine of 6 pi times 3. Well, sine of 6 pi is 0. Cosine of 6 pi is 1. In case you're wondering how to get that, 6 pi is basically going 3 times around the circle, but you stop where you started. So you stop and start at the point 1, 0. And 3, by the way, is still 3. So what do we have? Well, we have the square root of 4, which is 2, times 1 times 3, which is 6. Now our tangent line, and it's good to know the generic formula, so it's the function at your point plus the derivative at your point times x minus the point. So that's just the formula for what the tangent line would be at 2 pi. So we plug in what we need. So we get f of 2 pi, which is negative pi, plus 6 times x minus 2 pi. And there's our answer. All right. So, keeping with our theme of tangent lines, given that f of x is differentiable and that y equals 5x minus 6 is tangent to y equals f of x at x equals 2, y equals negative 2x plus 5 is tangent to y equals f of x at x equals 3, and y equals negative x plus 7 is tangent to y equals f of x at x equals 4, then find the tangent line to y equals f of f of f of x. Whew. Okay. So, what's going on here? Well, what's going on here is this understanding. This is really about tangent lines. So this problem is testing you fundamentally on, do you understand how tangent lines work? So here's the basic idea. If I have a tangent line at x equals a, then really that says I know exactly 2 things. I know what is f of a, and I know what is f prime of a. So that's the key, is if I have a tangent line at x equals a, I know these 2 pieces of information, and vice versa. And the way that this works is it's the formula we already mentioned, that y equals f of a plus f prime of a times x minus a. So we say, okay, fantastic. So what we're going to do is we're going to start with the information that was given to us, because we have tangents at 3 locations. From that information, we're going to extract information about the function. And now, once we have that information, we'll hopefully figure out how to get our new tangent. So, let's go through these one by one. So we have that y equals 5x minus 6 is tangent at 2. So, using this, we say, okay, how do we get our information? Well, to get f of 2, we plug 2 into the tangent line. So we get 10 minus 6, which is 4. F prime of 2, well, to get that, we read off the slope, because the slope matches the derivative. So that's 5. Now we have, well, negative 2x plus 5 is tangent at 3. So we can get f of 3 and f prime of 3. To get f of 3, we plug 3 into negative 2x plus 5. So we're going to get minus 6 plus 5, which is minus 1. F prime of 3 is the slope, so that's negative 2. And y equals negative x plus 7 is tangent at x equals 4. So that tells us we're going to get f of 4 and f prime of 4. So to get f of 4, we plug it in. Negative 4 plus 7 is 3. And to get f prime of 4, we read off the slope, and that's negative 1. So they gave us information about the tangent lines that translates into information about the function as we've listed here. So that's what we have in terms of f. Now, what are we after? Well, we want the tangent line to f of x at x equals 2. So that says I need to know what is f of 2. Well, let's just figure that out. This is an onion, and we just work through it one layer at a time. F of 2, well, f of 2 is 4, so that's f of 4. How about f of 4? That's 3. So that's f of 3. What's f of 3? Negative 1. Okay, so now we know what is the function of f of 2. The other thing we need to know is what happens when I take the derivative of f of x. So this is probably going to test our patience. This is really just the chain rule. We just have to work through it slowly, one layer at a time. So the chain rule says, start with the most outside. So in that case, the first f. Take the derivative of that, but you leave what was being put into it unchanged. So that's still an f of x. Now, go and say, what's inside of what you just took the derivative? In other words, I need to take the derivative of the inside part. So now I take the derivative here. That would be f prime. Leave the inside of that alone. But now multiply by the derivative of that inside, and that would be f prime of x. So this is chain rule and being very patient, working through it one layer at a time. So we need to plug in at x equals 2. So we get f prime of f of 2, f prime of f of 2, and f prime of 2. So we work through it. F prime of 2 is 5. F of 2, well, f of 2 is 4. And f prime of 4 is negative 1. F of 2 is 4. F of 4 is 3. F prime of 3 is negative 2. So we get negative 2 times negative 1 times 5, which tells us our derivative is 10. So now we have what's the value of the function, negative 1, and what's the value of the derivative, 10. So our tangent line, so going backwards, we can say that we get y equals the value of the function, negative 1 plus 10 times x minus the place where we're at, which is 2. And there's our answer. All right. Good. Well, it's not so bad. Now we step into something that we're probably a little bit less familiar with. And so this is going to be not so much a review, but just sort of a, here's an important idea. And the reason I say it's not so much of a review, we haven't quite covered this yet, but that's because we still have a few more lectures. But we're going to talk about it really quickly because the idea is really simple. So we're given that y prime equals 3/2 x squared y plus 3x squared 2y, and that y of 0 equals negative 1, and we want to find the function y of x. Now this is what's called a differential equation. Now how do you recognize this type of problem? Well, if you see a formula that involves both y prime and y in some way, so you have something equals something, and there's a y prime floating around and a y floating around, this is a differential equation problem. And so once you have that, you say, okay, how do we solve it? And the answer is there's one way to solve it. And this is what's called separable differential equations, and it's a very simple three-step process. So we'll write that down. The first step is to separate. The second step is to integrate. And then the final step is to uncomplicate. Now, uncomplicate is not a real word, but it was so nice. I had the separate and I had the integrate. I just had to come up with another word that ended with 8 that sort of fit. And uncomplicate, it almost sounds like it could be a word. So here we go. So what you do is you're going to think of this, instead of y prime, let's think of it as dy dx. So we get 3/2 x squared y plus 3x squared over 2y. So what happens when we say separate, what this really means is put all y's on one side and all x's on the other. That's what we mean when we talk about the separate. So we really want to say we're going to have one side of our equation is nothing but y's, the other side of our equation is nothing but x. Okay. So looking here, one thing we can do is we can say, hey, I can pull this out. Notice that there's x squared on both of these. In fact, I'll put out 3x squared on both. They might say, why the 3? Well, the reason why I want to pull out the 3 is because 3x squared is really nice, because I know my next step is going to be to integrate. So I really want to keep it so that I have something that's really easy to integrate, and 3x squared is really easy to integrate. What's left? Well, I have y over 2 plus 1 over 2y. Now, let's go ahead and add these together. I just need a common denominator of 2y. So that's 3x squared. And then what do we have? Well, we'll have y squared plus 1 over 2y. Now, remember our goal was put all y's on one side and all x's on the other. So here's how we're going to do it. We're going to now no longer think of dy dx as just a single item. We're going to think of it as actually something like a dy and something called dx. So we're going to think of this as two things. And you're probably thinking, Steve, you kept telling us that you can't do that. And I know. But we'll pretend like we can, because it makes the process much simpler to follow. So I'm going to multiply both sides by dx. And then I'm going to divide both sides by this y squared plus 1 over 2y, which really means multiply by the reciprocal. So if you do that, you'll get 2y over y squared plus 1 dy is equal to 3x squared dx. All right, and this is the end of stage 1, which is the separation stage. Now we begin stage 2, which is the integrate stage. And in this stage, what you do is you integrate. So that's easy to remember. Now, in particular, there's maybe one small thing I'll say, and we'll get there in just a second. So we integrate both sides. Well, this side is pretty easy. What's the integral of 3x squared? I'll ask you. X cubed, yeah. So we get x cubed. And of course, if you integrate, plus c. Now you do it to the other side. Now the other side, 2y over y squared plus 1. You might say, I'm not really sure. It's not one of my basic integrals that I know. But you can do a little work on the side. If you set u equals to y squared plus 1, which is the denominator, you would get that du equals 2y dy, which is the numerator. Because notice this is not the arctangent. Arctangent wouldn't have a y upstairs. So if you did that, what would you have? You'd have the integral of 1 over u du. And the integral of 1 over u, that's on our list. It's log of u plus a constant. So that means over here, we put it back. The integral here by itself would be log of y squared plus 1 plus a constant. So what do we put down here? We put in log of y squared plus 1. And now you're like, ooh, Steve, you forgot something. You forgot your plus constant. I actually didn't forget. So here's the thing, is if I had a constant here, but I also have a constant here, I'm over-constanted. Wait, that's not a real word either. Okay, I need to stop making them words. I can put the two constants together into sort of one big uber constant is the moral. I only need one constant for one of the sides. I don't need to have constants for both sides. So just need 1 plus c. Pick your side, whichever side, but you need one of them. All right, so that comes to our final stage, which is the uncomplicated. And since that's not a word, I really have to talk about what I mean by that. And really there's two things. You need to solve for your constant. And then the other thing you have to do is to get y by itself. Now, you actually have some choices here, because there are two processes that need to happen, and they can happen in any order. So in other words, first you can solve for y, and then you can solve for your constant, or first you can solve for your constant, and then you can solve for y. I usually like to solve for my constant first, and you might say, okay, how do we solve for our constant? Well, there's something that we haven't used, which is this piece of information. The fact that y of 0 equals negative 1. So what that tells us is that when we plug in x equals 0, we get y equals minus 1. So we're going to take this information and plug it in over to here. So we plug that in, we get natural log of negative 1 squared plus 1, which is 2, is equal to 0 cubed plus c. So that tells us that c is equal to natural log of 2. So now we have our constant c. All right, well, Now that we have our constant, our last thing is to solve for our y, because we want to get y by itself. Right now, y is sort of not by itself. So to get it outside of the log, use the exponential function. E to the log of y squared plus 1 becomes y squared plus 1. Then I have e to the x cubed plus log 2. Now for this, there's a really nice thing you can do, which is that's e to the x cubed times e to the log 2. And what can you do with e to the log 2? Well, that's 2. So this is 2e to the x cubed, because e and log are inverse functions of each other.
How come it's not e to the x cubed plus e to the ln 2?
Well, we're just taking the exponent like that. So rules for exponentiation, remember, say, if I have addition in the exponent, it becomes multiplication down here. All right, so we're almost there. See, we're getting close. We're sort of just chipping away at it. So what is y squared? Well, that's 2e to the x cubed minus 1. And finally, we take the square root. So y is the square root of 2e to the x cubed minus 1. But wait a second, when you take a square root, it's plus or minus. The question becomes, do we know whether it's the plus or whether it's the minus? We can't have two solutions. There has to be only one. There can only be one. Can we figure out which one it should be? Well, let's go back to our initial condition. Remember, this has to be satisfied. So I need to have, when I plug in 0, I get a negative out. So do I need to keep the plus or the minus? I got to keep the minus. So be careful. Be careful. If you're ever faced with a, I have plus or minus, look back to your initial condition and it will tell you which way to go. So that tells you that this is the unique function which satisfies the original equation given to us together with the initial condition given to us. So separate, integrate, uncomplicate. And we'll get more practice with that later on this week. Okay. So now to our next problem. Find the limit as t goes to 0 of sine of t over t to the power 1 over t squared. Now, there's a couple of things going on here, but let's just talk about this one. We see the word limit. Now, if you see the word limit on this exam, you should automatically say to yourself, or maybe not even say, start going, ho, 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 ho. You should be, this is l'hôpital. Because if you look at the topics that we have narrowed the exam down to, the only place where limit shows up is l'hôpital. So if you see a limit, you're like, okay, I am betting l'hôpital comes into play. So be ready to use the rule. So we're going to talk about this. Now there's something else that we see here, and this is just good to know. When you see sine t over t, it's just, this is a fact that hopefully you'll remember, and if you don't remember, let's hope we give it to you. But what happens to sine t over t as you go to 0? Do you remember? Goes to 1. 1. It's a really important limit. So when we see sine t over t, it's good to know that that's equal to 1. It's a useful tool. Of course, it doesn't really matter that it's t. It could be anything. As long as the inside matches what's underneath it, then it goes to 1. Okay, so let's see what's happening here. So the way you use l'hôpital is you first say, what's happening if I just plug it in? In fact, that's the way you do everything. Is you always say, well, let me just plug it in. And I say, okay, well, what's happening? Well, sine t over t, that's going towards 1. 1 over t squared, well, since t is going to 0, 1 over a very small number is going to be huge. So it's going towards 1 to the infinity. Now, 1 to the infinity is what's called an indeterminate, which is just a fancy way of saying we don't know what it is. We have to have more information. And that's one of the things that we need limits to figure out. So when you see an indeterminate, that's the clue that you need to do l'hôpital. And if you're going to apply L'Hopital, remember you always have to make sure that it is an indeterminate. If you just start applying L'Hopital without checking, you're going to lose some credit. So we don't want to do that. We want all the credit. We work hard for these answers. We deserve the points. All right, now we want to say, cool, apply L'Hopital. But the problem is you can't apply L'Hopital here. Because remember, L'Hopital needs to have a fraction. So to get from this kind of expression to a fraction is where we would use a log. So suppose we say our answer is L, and we use the natural log. Now, I'm not claiming that you are going to necessarily need to do the following, but this is a nice thing to remember. Logs are useful for bringing down exponents. They're an incredible tool, amazing tool, really. So this becomes the limit as t goes to 0 of the natural log of sine of t over t to the 1 over t squared. And whoops. Okay, I should put some more parentheses. All right. So when I use the properties of logs, I can rewrite this. This is the limit as t goes to 0 of natural log of sine t over t squared, which is going to 0 over 0. Because we already know that sine t over t goes to 1, and log of 1 is 0. So that means we can apply L'Hopital. But before we apply it, whenever I see a log of a division, I say, well, before I do anything with our derivations, our derivatives, I'm going to first simplify it by breaking it up. So log of sine t minus log t over t squared. So now I apply L'Hopital. So make sure that you check that it's indeterminate, and then indicate somehow that you're applying L'Hopital. So I'm putting LH. You can actually write out the words, I'm applying L'Hopital. Give me my points. Well, you don't have to say, give me my points. That sounds greedy. But you can say, I'm applying L'Hopital. It's a beautiful day. It's a beautiful day. It's a wonderful day on the Champs-Élysées. I don't know if that's a real thing, but it sounds very French, you know. And what do we have? Well, we take the derivative of the top and the bottom. Well, downstairs, that's an easy derivative. Remember, this isn't a quotient rule. Take derivative of the top and the bottom. So we get 2t downstairs, derivative of sine, log of sine. Well, derivative of log is 1 over, plug the inside in, times by the derivative of the inside, which is cosine, minus 1 over t. Now, at this point, it's not so clear what's going on. Let's clean this up a little bit here. So, what can we do? Well, upstairs we can write this as, there's always the limit. By the way, notation matters. And yes, we do take off points for bad notation. So if we get a common denominator of t times sine t upstairs, that would be t times cosine t minus sine of t divided by t times sine of t. That's the numerator. The denominator is 2t. So this becomes the limit as t goes to 0 of t cosine t minus sine t, all divided by 2t squared sine t, if I just move that 2t up. Now at this point, what happens? Well, let's just do a quick check. What does this go to? Upstairs, it goes to 0 minus 0. Downstairs, lots of zeros. So it goes to 0 over 0, which means we can apply L'Hopital. And before I get too much further, I don't want to make you super nervous. I chose this one because I thought, you know, this would be really fun to see how much we can actually do. Not because I thought this would be necessarily the same level of difficulty. I prefer to put review problems that are more challenging than exam problems. So if in the next couple of minutes you're like, is this really what we're going to have to do on the exam? The answer is probably not to this extent. You should be able to do L'Hopital. Almost surely something nicer will happen. And you're probably thinking, what's about to happen that he has to preface all this? Let's find out. It's going to be a wonderful thing. Wonderful thing happening. I hope. Okay, so we apply L'Hopital. Limit as t goes to 0. And now we just be patient. So upstairs, product rule. So we get cosine t. Then we're going to get minus t sine t, and then we're going to get minus cosine t. And then downstairs, we're going to get what? Well, 2t squared, rid of that is 4t times sine t, plus 2t squared times, rid of sine, which is cosine. So clean it up. The cosines, they cancel. So that's a good thing. But something else also can cancel. Notice I have a t there. And there's a t there, and there's a t there. So every term that's left has a t involved. So I'll cancel off a single t off of every one of those terms. So at this point, let's see what we have. We have the limit as t goes to 0 of upstairs we have negative sine of t. And downstairs we have 4 sine of t plus 2t cosine of t. All right. Well, let's see what happens. What does this go to? Well, the numerator, sine is 0, 0. Downstairs, sine is 0, 0. And 0 is also 0, so it's 0 over 0. So what do we do? Well, we do it again. Well, Now, normally, by the time you hit your third one, you start to get nervous. The derivative of negative sine is negative cosine. And now we're not nervous. Because what? It's game over. Game over. Because cosine at 0 is not 0. So we know whatever happens, happens now. So the derivative of 4 sine t, that's 4 cosine t. Product rule, 2 cosine t minus 2t sine t. And what do we get? Well, again, 0. But as we said, cosine of 0 goes to something, negative 1. Downstairs, we get 4 plus 2 minus 0. 6. So negative 1, 6. Now, is our answer negative 1, 6 for our limit? No. Yeah, you see that, right? Because what you do is you start going back and say, well, what is it? What is it? And you run all the way back and say, that's the log of our answer. And therefore, our answer, and it's the answer to our original limit as t goes to 0, sine t over t to the 1 over t squared is equal to e to the negative 1 over 6. Exactly what we would have thought when we started. Well, maybe not exactly. So that's why we did the work. All right. Number 6. So let's let f of x equal x squared e to the negative 3x divided by x squared minus 3. And we want to determine the intervals where the function is increasing and where it is decreasing, and classify any critical points. So, a couple of key things here. When you see increasing and decreasing, that's an indicator that we need to be talking about the derivative. So whenever you see increasing, decreasing, you know I'm dealing with the derivative. In particular, f prime is positive corresponds to increasing, and f prime being negative corresponds to decreasing. Now, you will get conflicting statements about what to do when f prime equals 0, whether to include endpoints or not include endpoints. And at this point in time, you should not think about this and dwell on this too much. The answer depends on your technical definition. We are not going to test you that finally. Essentially, the moral is, as long as your derivative is positive, you're increasing, and as long as it's negative, you're decreasing. That's how you should think of it. And if you have two things which are increasing right next to each other, you put them together, and life is good. There's also this classify critical points. And we'll get to that classifying critical points once we're there. But at any point, we know where we need to go with this problem. We have to go into the derivative. And so let's take f prime of x. And I guess I should pause here and say, how do you take this derivative? You can use the quotient rule, but you don't really have to. One thing you could do is you could think of this as x squared minus 3 to the negative 1 power. And so if you're not a big fan of quotient rule, the good thing is you really don't need to know the quotient rule. Just think about taking whatever is downstairs and raising it to the negative 1 power, and then you just do a product rule. And notice this is a product rule with 3 pieces. And so whenever you have a product rule, the moral is everybody gets their turn. So we say, all right, whoops, that's f of x. See, there you go. See, that was a very fancy f. So what is f prime of x? Well, you say the first one gets its turn. So 2x, the other 2 stay as they currently are. E to 2x, e to negative 3x, x squared minus 3 to negative 1. Now, the middle one gets its turn. So that would be negative 3 e to negative 3x times x squared minus 3 to negative 1. And be generous with your parentheses. A lot of people forget to write down parentheses, and then 20 seconds after they wrote it, after they didn't write it, they forgot, oops, there's actually a parenthesis there, and they misinterpret it, and then they lose points. We don't want to lose points. That's not why we're in calculus. We came to get points. Last one. Minus comes down, x squared minus 3 to the minus 2, and then times the root of the inside, which is 2x. So there's our derivative. Factor out what they have in common. Well, what do they have in common? Well, they all have an e to the negative 3x, so that's something we should definitely be pulling out. They all have at least x, because I see an x, there's x squared, there's actually x cubed there, so I'm going to factor an x out. And they all have x squared minus 3, and I'll pull out the lowest power, which is negative 2. And once we factor that out, we go through and we say what remains. Well, from the first term, well, there's the 2, and the e to the negative 3x and the x we've got, the x squared minus 3 to negative 1 will become x squared minus 3 to the positive 1. Because if you pull negative 2 out, but there's only negative 1 to begin with, you have to compensate by putting plus 1 in. Or if you like, another way to think about it is you take the exponent and subtract what you pulled out. Negative 1 subtract negative 2 is negative 1 plus 2, which makes 1. From the middle term, well, we're going to have that minus 3. Then there's going to be an x. And then there's, again, x squared minus 3. From the last term, well, we're going to get minus and a 2. And what else? Well, we pulled that x out, so there's still an x squared. And I think that's everything, because we got the x squared's there, the e negative 3x pulled out, x squared minus 3 negative 2 pulled out, negative 2. Yep, it's all there. So let's clean this up. That's x e to the minus 3x. All right, this says x squared minus 3 quantity squared downstairs. And if we expand this out, we get 2x squared minus 6 minus 3x cubed plus 9x minus 2x squared. And I'm hopeful that I did not make another mistake here. This is, well, we keep going, right? You got to have faith. If you don't have faith, it's not going to work out. All right. Well, the 2x squared minus 2x squared, well, at least that cancels. That's some good news for us. So let's see. We got x e to the negative 3x divided by x squared minus 3 squared. And actually, let's look at these terms. Notice that what remains, everything is divisible by 3. So let's go ahead and pull out a negative 3. And what remains after we've done all that is x cubed minus 3x and plus 2. Now we come to the problem. Well, we need to know the zeros. So we really need to dig into x cubed minus 3x plus 2. Generally speaking, we can't factor cubics. But of course, we're not going to give you problems that are just any coincidental problem. So we say, all right, if we are faced with a cubic, one or two things happens. Either it's a cubic we can work with, or we made a mistake. Before I go back and look for my mistake, I'm going to say, well, if it's a cubic I can work with, it means it has to have a super, super easy root. So I look at this and say, okay, super, super easy means things like 0 or 1. Well, it's not 0. How about 1? Well, we plug in 1. What do we get? We get 1 minus 3 plus 2. So that means that 1 is a root. All right? So I can write this as x minus 1. So if I know one root, I can say, okay, it factors, and x minus 1 is a factor, since 1 is a root. Now at this point, you can do a little bit of reasoning, or if you don't like reasoning, you can also do long division. I prefer to reason. So what do I mean by reason? Well, notice that there's no x squared term. Well, if I take minus 1 times x squared, that's the negative x squared. Well, I got to cancel that negative x squared, and the only way I can do it is with the x multiplied by whatever this is. So that would only work if this was a plus x. So that's my reasoning. It's like, okay, I can get the lead term here. The reason I know there's an x squared in front is I have to get to x cubed. The reason there's a minus 2 at the end is I have to get to 2. And then I say, okay, let's look at either the x squared or the x term and use that to reason what does the last piece in the middle have to be. Now we get down to a quadratic, and quadratics we have a better chance with. And if you look at this quadratic, you have a really good chance with this quadratic because it factors. It's x plus 2, x minus 1. So now we can say our derivative, our f prime of x, took us a while to get here, but it's negative 3x e to negative 3x, x minus 1 squared, x plus 2, divide that by x squared minus 3 squared. Okay, good. Now we come to where are the important points. So in particular, the critical points. These are the points where the behavior in terms of increasing, decreasing can change. So we go through and we list them. So we look. Well, the good news, e to the negative 3x can never be 0. So that's good. So we get 0, 1, and negative 2. Are there any other critical points? Well, the answer is yes, because you also need to look for where the derivative is undefined. And notice this is not a plus downstairs. X squared minus 3, which means we also have critical points at negative root 3 and positive root 3. So there are 5 critical points. Now our function is undefined at root 3 and at negative root 3. And so we are not going to talk about them as in terms of being we're not going to classify them because they're actually not part of the function. But when it comes to increasing, decreasing, we do need to pay attention to them. So we list these in order. Negative 2, negative root 3, 0, 1, root 3. Square root of 3 is between 1 and 2. And then the reason it's between 1 and 2 is that 1 squared is 1, 2 squared is 4, and 3 is between 1 and 4. And now the way you do this is you just go through and you test the intervals and you pick numbers. And you can pick numbers and then you can just talk about behavior changes. So, for instance, suppose you pick like a huge number out here. Well, if you look at your expression, your denominator is always positive. The e to the negative 3x is always positive. The x minus 1 squared is always positive. So the only thing that really determines the behavior is you have a negative in the front and the x and the x plus 2. Everything else is positive. So if I pick a huge positive number, I'll get a negative, positive, positive. So that tells me that my derivative is negative. If I'm between 1 and root 3, well, nothing's changed. Because I'm still going to be a negative, positive, positive. So I'm still going to have negative. Between 0 and 1, it's still negative, positive, positive. So I'm still negative. Between negative root 3 and 0, well now the 0 flips the sign. So it's negative, negative, positive. So I am increasing. From negative 2 to negative root 3, well, because the negative root 3 doesn't affect the sign, I'm still positive. So it's still positive. And if I'm a really large negative number, it's negative, 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 which means that the derivative will be negative. So, what do we have? Well, in terms of increasing, and be careful here, you really need to separate this. Negative root 3 and positive root 3, that breaks your function into 3 parts. So don't try to merge over those pieces. So increasing from where? Well, from negative 2 up to negative root 3, and I don't include negative root 3 because it's not part of the function, comma, negative root 3 to 0. And again, don't worry about the endpoints. If you want to be safe, just don't include endpoints, and then you don't have to worry about it, and then everything's fine after that. Decreasing. Well, let's see. We're decreasing from negative infinity up to negative 2. And okay, that's positive, negative. Okay, so that's from 0 up to square root of 3. And I don't include square root of 3 because it's not part of the function. And then from square root of 3 on to infinity. So finally, for our classification, we have 3 points which can be classified. Negative root 3 and root 3 aren't classified because they're not part of our function. So how do you classify? Well, the answer is we use the first derivative test. And the first derivative test says, look at the behavior on both sides. So at negative 2, we are going down, and then we are going up. So when you see the derivative going from a negative to a positive, that means your function was going down, now it's going up. So negative 2 is a local min, because down, up. At 0, we were going up, and then we were going down. So that says that 0 is a local max. So when you go from a positive derivative to a negative derivative, you pass through, that says that you're a local max. Now if you look at 1, you go down, down. Well, if you go down and you go down again, that says that 1 is neither min or max. And that's a possibility. So if your derivative just happens to touch the axis but doesn't cross, then you're neither a min or a max. So you can remember the first derivative test, but a lot of it is just intuition. Just think about what is the first derivative telling you about the behavior. And once you understand that, life is good. All right, next problem. Find the area for 0 less than or equal to x less than or equal to pi under the curve y equals 1 plus cosine x squared of 1 minus sine squared x. Of course, this is talking about area. So whenever we see an area problem, what do we do? Well, area is integration. Now, in this case, when we talk about under the curve, what we really mean is under the curve is just secret code of saying down to the axis. Now, the reason I say down is ideally it should always be positive. And you can look at our expression, and it has to be positive because cosine of x is always between negative 1 and 1. So 1 plus cosine x is never negative. The square root of 1 minus sine squared x is never negative. So it is a positive function. Now, in this case, the bounds were given to us. They said between 0 and pi. Yes?
If it wasn't a positive function, do we have to do anything different?
Well, they would phrase it differently. It wouldn't be phrased this way. I don't know how they would phrase it. One way they would probably phrase it is find the area for absolute value of this, or something like that. So the comment I wanted to get to was the bounds. In this case, they gave the bounds, and so we're great. Now, if they hadn't given the bounds, that doesn't mean we can't do it. We can find the bounds. So if the bounds are not given, how do you find the bounds? Well, this is not really relevant to this problem, but I just want you to make sure that you can handle anything we throw at you. So what you look for is if it's just a single function, you say when would the function hit 0? Because you can always think of your other function as being the function 0. If it's 2 functions, you say, well, when do the 2 functions cross? So if your bounds aren't given, just keep in mind that means you have to provide the bounds. And oftentimes, you also have to do the extra step in saying which one is larger. So that's not too bad. I hope. We'll find out. So we have an integral problem. So we want to find the integral from 0 up to pi of 1 plus cosine of x times the square root of 1 minus sine squared of x. Now, if you've been following along, or maybe if you did a bunch of recent quiz problems, you're like, oh, ha ha ha, he's going to put a circle in here. Maybe we are. Maybe we love circles. Let's see. Now, the intuitive thing to do is to say, hey, I should make a substitution. The substitution should be sine. What's the derivative of sine? Cosine. And then we say 1 plus. What? That 1 plus is messing things up for us. So here's a neat fact about integration. See, integrals have this cool thing which is called addition, which means that you can break integrals up. And sometimes the integral that's given to you, you don't want to do one thing to integrate it. Maybe you have two different tools that need to be used, and you need to break it into two different parts. So in particular, what I'm talking about here is this is the integral from 0 to pi of, if I distribute this through, square root of 1 minus sine squared x plus cosine of x square root of 1 minus sine squared x dx. Oops, sorry. There we go, dx. Which means I can think about this as two separate integrals. Integral from 0 to pi, square root of 1 minus sine squared of x, plus integral 0 to pi of cosine of x, square root of 1 minus sine squared of x. Now, we can handle them separately. So the substitution for sine doesn't quite work here because of the fact that there's this 1 plus. But it works great in this setting here. So if you set u equal to sine of x, then we get that du, that's cosine of x dx. So we see our du. So we get that this piece here becomes the integral of square root of 1 minus u squared du. But now let's do the bounds. All right, so we plug in 0. Sine of 0 is 0. Plug in pi. Sine of pi is 0. And the integral from 0 to 0 of the square root of 1 minus u squared is 0. Goes away. We didn't have to do any circle there. Oh, that's kind of sad. Well, maybe the other part is the circle part. Yes?
You repeat why you didn't use sub 1 minus sine squared?
Well, why did I not use sub 1 minus sine squared? Well, if you try to do a u substitution for 1 minus sine squared x, take the derivative of 1 minus sine squared x, and what you'll get is, you have to do the chain rule. The 1 minus, the 1 and the minus don't really matter. The 2 comes down, you get sine x, cosine x. And we have the cosine x, but we don't have the sine x available to us. And so because we didn't have that sine x ready, that's why we didn't make that substitution. Okay, so how do we handle the first part? Well, we can't do the substitution for sine because there isn't a cosine. We can't do the substitution for sine squared because there's still not a cosine and also not a sine. And at this point, you're like, well, then maybe we have to stop. We can't do it. But now we do one other fun thing, which is called trig identities. 1 minus sine squared x isn't just anything. It's cosine x. Or rather, I should say it's cosine squared x. And so trig identities are really important. In fact, they're one of your big tools when it comes to rewriting integrals. You have your basic formulas that you know you can integrate. You have algebra, you have trig identities, and then you have substitution. So it's good to know your trig identities. Square root of cosine squared x. Well, cosine x, I think. Integral of cosine is sine. And evaluate from 0 to pi. So we plug in pi. What do we get? Sine of pi, which is 0, minus sine of 0, which is 0, which is 0. So that means there's no area? Now, at this point, you should be highly suspicious. You should think, I think Steve has made a mistake. The question is, did he do it deliberately or not? Well, there is a mistake. I'm going to give you a few seconds. Can you spot where the mistake is? Was there a mistake over on this side? Or was there a mistake on that side? The answer is, it was right here. Square root of cosine x is not cosine of x. What is the square root of cosine squared? It's absolute value. So, what's happening? Well, when you square something and take the square root, what happens is you lose the sign information. Squaring something is always positive, so when you take the square root, you're going to end up with something which is only positive. So normally cosine of x between 0 and pi looks like this, which is why when we did the integration we got cancellation, because this part and that part canceled out. But when we take the absolute value, we say, oh, we really need that. So we don't need them to cancel, we need them to combine. So that's what we needed. So now that we understand that, we say, oh, okay. So really this should have been, continuing on, let's just do twice what we get from as we go from 0 to pi halves, because we know what cosine looks like. Now, if you're paranoid, you could do 0 to pi halves and pi halves to pi, where we change it from negative. So this might be that, how do you handle the negative underneath? Well, you put negatives in front. So this is 2 sine of x from 0 to pi halves. And now when you plug this in, you get 2 sine of pi halves minus 2 sine of 0. Sine of 0 is 0. Sine of pi halves is 1, giving us the final answer of 2. And no circles were harmed in the solution to this problem. All right. Number 8. Given that f of x and g of x are differentiable, and that h of x equals f of x times g of x, and k of x equals f of g of x, we want to fill in the missing entries in the following table. So here we have this table where a lot of entries are not there. So in other words, we've given you information, and we want to say, well, use what is available to you and fill the pieces of information in. Now, one way you can do this is sort of keep banging your head against the wall and sort of say, how about this, how about that? Suppose you wanted to be methodical. Well, if you wanted to be methodical, you can say, I know that these pieces over here, which are our h prime, our k prime, really are formed from our f and our g. So let's write everything that we can in terms of f and g. So we should make some notes here. We can say, well, h prime of x, that's equal to f prime of x times g of x plus f of x times g prime of x. In other words, it's the product rule. And the product rule is a super important rule. So we want to make sure we know that. K prime of x, that's f prime of g of x times g prime of x. So let's look at the entries that we have here. I'm going to just write these entries down. So we have, this is h of 2. That's f of 2, g of 2. And we have that h of 3 is f of 3, g of 3. And I'm not saying that when you do this problem you have to do it this way, but I'm just saying if you were not sure what to do, this is one idea. It's just to say, let's be methodical and let's write down what everything is in terms of the basic building blocks. Because our basic building blocks in this case are really f and g. So if we can figure out everything in terms of f and g, or rather how everything relates to f and g, then life is good. So that's why I'm writing all this down. So once we get there, then we can start sort of piecing everything back together. And you might say, how are we going to use this information that we're writing down? The way we're going to use it is we're going to say, well, what do we know? And then if we ever say, oh, I know everything except one fact, that gives me a fact. So let's see, what do we know? We know currently, what is f of 2? So everywhere where I happen to see in f of 2, I can just mark that. We also know h of 3, so I'll mark that. We also have to know k prime of 3. I hope that's showing up. Yeah, it's showing up enough. Okay. All right, we know f prime of 3. So everywhere where there's an f prime of 3, not that many places, we know g of 3. And there's a few places where g of 3 does show up. We know g prime of 3, so that's good. G of 3 actually shows up here. Okay. And let's see, how are we doing? Let's see, g prime of 3, also shows up here. And we know h prime of 3. And we know k prime. Okay, I think that's what we know right now. So let's look at this and let's point to things. So here's something. Notice that we know h of 3 and we know g of 3. And so that says, okay, what can this tell us? Well, this equation here, that tells us that h of 3, which is negative 3, is equal to f of, why did I mark this one? We don't know h of 3. We know h of 2. That was a terrible mistake. All right, unmark that one. H of 2. We know h of 2. So h of 2 is negative 3. That's equal to f of 2, which is negative 1, times g of 2. So what's our conclusion about g of 2? G of 2 equals 3. So now we say, okay, now we know what g of 2 is. So we can update. So we now know what g of 2 is. And so now we're like, aha, we can now solve more things. So let's think about this. Well, g of 2 is 3. And so this would be f prime of 3. And oh, wait a second, I happen to know what f prime of 3 is. So we actually can find this whole expression. G of 3 is 2. I don't know what f prime of 2 is. Well, wait a second, though. We can use this. See, look, there's only one thing I don't know. So what is that? Well, k prime of 3 is negative 15. That's equal to f prime of g of 3. So that's f prime of 2 times g prime of 3, which is negative 3. So if I use this piece, what can we conclude? Well, that tells us what? It tells us that f prime of 2 is 5. So that goes there. So now we know f prime of 2. And we start thinking to ourselves, okay, does that give us anything? Well, it gives us a little bit. That's for sure. But we say, oh, hey, here's something. We already used that. Here's one. H prime of 3. Notice that we have everything except f of 3. So we plug in what we know. So h prime of 3 is 2. That's equal to f prime of 3, which is 7, times g of 3, which is 2, plus f of 3, which we don't know, times g prime of 3, which is negative 3. Okay. So we get 2 is equal to 14 minus 3 f prime, that's not f prime, that's f. So we can rearrange. We'll get 3 times f of 3 equals 12. And therefore, f of 3 is equal to 4. All right. Now we're really close. So we know what f of 3 is. So now we can finally come here, since we know f of 3. H of 3 is f of 3 times g of 3. So that tells us that h of 3 is 8. Let's see. What haven't we used yet? Well, do we know g prime of 2 yet? And h prime of 2? Nope, not yet. Here's something. Let's see. Can we figure this out? Do we know k prime of 2? We do. Why wasn't it marked? Well, let's mark it now. So if we mark this, what do we get? Well, So k prime of 2, that's a huge number, that's 42. That's equal to f prime of g of 2. Well, g of 2 is 3. Okay, times g prime of 2. What's f prime of 3? Well, f prime of 3 is 7. So 42 equals 7 times g prime of 2. So 6 equals g prime of 2. So that's 6. And now we're like, perfect. Now we can find h prime of 2. So how do we do that? Well, we just plug our pieces in. So our final thing is that h prime of 2 is equal to f prime of 2, which is 5, times g of 2, which is 3, plus f of 2, which is negative 1, times g prime of 2, which is 6. So we get 5 times 3, which is 15, minus 6, which gives us 9. And that's our answer. So that's the chart. So if you just saw this and you were like, how do we do this? You could play around and maybe you'd fall in and find some coincidences. But if you do it more methodically, say, okay, look, let me write down all the relationships. Because what we're doing here in this solution is we're saying, let's write down all the relationships that we know and figure out what pieces do we have enough of to fit together. And keep track of things as it evolves. And if we keep track of enough, then we might find our answer. So this is a fun problem. One of those ones. So on a lazy Sunday afternoon, you wanted to do a nice calculus problem, pull out a problem. That would be good. Okay, find the following integrals. So, the integral of cosine theta over 2 minus cosine squared theta d theta. Now looking at this problem, it's not entirely clear what to do. First off, it's not on our list, basic list of integrals that we should know. So we say, okay, that means we need to do something to it. And it's clearly a trig problem. So we're like, all right, we need a trig identity. But before we go too far down that road, very likely we'll need to do a substitution. So one of the things you should start getting to the habit of doing is to say, can I see a good substitution early on? And the sooner you can see a good substitution, that can help guide you in making decisions about how to rewrite things. Is there a good substitution to make? Well, when you're thinking about substitution, and you definitely at some point while you're taking the exam will want to think about substitution because it's the go-to tool for integration. So when you're thinking about substitution, you should always say, when I'm thinking substitution, there's two places for me to be looking for. And the two places that you want to look are the places where you have a part showing up. So they are specifically, you look for a function on the inside, and that can be easy. Sometimes it's really clear, like, oh, this is a function in a function. Like if I have log of a function, okay, I clearly have a function, log, and there's another function inside. Sometimes it can be subtle. But the other thing to look for, and ideally you should have both things happening, is you say, oh, I spot a piece that's the derivative of something. So I know my integrals, but I also know my derivatives. And so I'm looking at this and I say, okay, there's a cosine theta and a 2 minus cosine squared theta downstairs. And I say, do any of these pieces, do they show up on my list of things which I happen to know are a derivative of something? Well, the answer is the cosine theta shows up, right? So if you think about it, the derivative of sine gives us cosine. So this cosine theta in the numerator is suggestive. This suggests we should be trying to write it in such a way that we can make a substitution for e equals sine. So now that we have that suggestion, we now have our mindset, well, in order for us to do that, we need to make sure everything is in terms of sine. And right now we have that 2 minus cosine squared. So we somehow now say, all right, how do we get so that that 2 minus cosine squared is just in terms of sine? So now we start to flex our trig identities. So we're going to keep the cosine as cosine. And now there aren't too many trig identities you have to know. So what's one of the ones that you do need to know? Well, we'll write down the ones that we expect you to know. Sine squared plus cosine squared equals 1. Tangent squared plus 1 equals secant squared. Sine 2 theta is 2 sine theta cosine theta. And cosine of 2 theta equals cosine squared theta minus sine squared theta. And if there's anything more complicated than those that you need, we will give it to you. Those are not that many formulas from trigonometry. And the first two are Pythagorean theorem. And so a squared plus b squared equals c squared, when you just re-express it in terms of trig functions, becomes the first two. So here we see, okay, there's a cosine squared, and look, lo and behold, it's attached to sine squared. So I can replace cosine squared by 1 minus sine squared. And so this becomes the integral. If you clean it up a little bit, oh, don't forget your d theta. Make sure you follow your notation all the way through. Keep your d thetas with you, because these graders, they are really particular. And it's important that they are, because if you get into the good habits now, it's going to pay off later when notation becomes much more important. Now we're in our proper setting. We wanted to write everything in terms of sine except for that cosine, because our cosine is going to become du. So we are prepared for our substitution. U equals sine, du equals cosine. So d theta. So this becomes the integral du over 1 plus u squared. And once you get to here, you say, is that on my list of 8? And the answer is absolutely. It's a beautiful entry on our list of 8. That's arctangent of u. And because we want all our points, if it's an indefinite integral, make sure you put your plus c. And because it's an indefinite integral, you have to go back. So we don't have to go very far. We've got to go back to theta. So our final answer for the first one is arctangent of sine theta plus c. All right. So there's the first piece, leaving us not a whole lot of room for part 2. Okay, so now part 2. Find the integral of 1 over y squared plus 1 minus the square root of y to the 4th plus 2y squared dy. This one's more challenging. All right, so the first thing you might ask yourself, is this on my list of 8? And pretty quickly you're going to say no. Because this is not, if you were going to write down 8 functions, be one of the first 8 functions you write down. So you say, okay, so I got to do something. There's absolutely no trig anywhere to be seen. I don't see any good substitution to make at this point in time. And so that leaves us with algebra. And we say, all right, algebra. Well, we notice, at least if nothing else, we would like to get rid of that square root in the denominator. Because if we can get rid of the square root in the denominator, maybe we have a chance. So what's our favorite tool for helping us get rid of square roots? And it's not squaring. Conjugate. So the conjugate. That's an algebra technique. And a lot of calculus is really just algebra with extra steps. So when we think conjugate, we're going to think of like a minus b multiplied by a plus b. In this case, I'm going to have just the square root part is one part and the other part. So this is like a minus square root b. So we're going to have that this is, give ourselves a little bit of space, 1 over y squared plus 1 minus the square root of y to the 4th plus y squared times y squared plus 1 plus the square root of y to the 4th plus y squared. And upstairs, y squared plus 1 plus the square root of y to the 4th plus y squared. All right, so conjugate, a plus b, a minus b. And the reason we do conjugates is when you take a plus b times a minus b, you get a squared minus b squared. So upstairs, we get y squared plus 1 plus the square root of y to the 4th plus y squared. Okay, downstairs, we're going to get y squared plus 1 quantity squared minus, And when we multiply these terms together, the square root goes away. Y to the fourth plus y squared. Okay, so a plus, did I make a mistake?
Yeah, I think you're missing a 2 on the 2y. It's the square root of...
Oh, you're right, I am missing a 2. Ah, that's probably going to be important later on. Thank you for pointing out my mistake. Yes. Well, I'm sure I would have seen in just a second when it's like, whoop, that's not working. Okay. But appreciate the knowing now. This is not looking much better. But remember, algebra, you got to be patient with it. You got to be gentle. Bring it some flowers. Take it out on a nice evening and say, look, let's work together and let's have a better relationship. Okay, so we got to keep working it. So let's keep it down here. Focus our energy on the denominator, because the denominator is almost always the challenging part. When things are upstairs, we're pretty happy with them, and there's a lot we can do. When things are downstairs, it's like, ah! Okay, so we'll start by squaring. If we take y squared plus 1 quantity squared, that would be y to the fourth plus 2y squared plus 1. And then we're going to subtract y to the fourth and subtract 2y squared. And I said y to the fourth, but I wrote y squared. There we go. Y to the fourth minus 2y squared. And so if you look at your denominator, you'll see, whoa, it's 1. That's a lot better to work with. We like that denominator. Okay, so now our integral becomes the following. Well, we have y squared plus 1 plus the square root of y to the fourth plus 2y squared. Okay, at least that is a much more palatable integral to be working on. Now, if you think about it, whenever you have addition, that says you can really break it up into pieces. So let's break it up into 3 little pieces and talk about each piece. So we have the y squared dy, the 1 dy, because remember addition breaks up, and then we have this last piece. And before we write it down, let's think about where we could go with this. So it's the square root of y to the fourth plus 2y squared. Now, as it is, this is definitely not looking very circle-like because there's not a minus inside that square root. Usually when you think of circle, you see a square root of 1 minus something. So it's not circle. So it's not going to be a circle trig. And it can't be a circle trig because this is a indefinite integral. So that says the only way we're going to really be able to tackle this is to do more algebra and or substitution. The problem is there's nothing on the outside. What can we do to that expression to clean it up? We could pull out a y squared. So notice this is really the square root of y squared times y squared plus 2. And the square root of y squared is y. And yes, I do know that you're thinking, Steve, shouldn't it be absolute value? Just go with it. Don't stress too much about it. It's just y for now. All right. So let's talk about these integrals. The integral of y squared, well, that's 1/3 y cubed. No surprises. Integral of 1, well, y. All right, good. And I should point out the integral of 1, I'm integrating with respect to y, so that's why it's y. Don't say, oh, it's x. No, y is our variable in this case. How do you integrate y times the square root of y squared plus 2? Well, you probably can see it. Substitution. So here you let u equal y squared plus 2 du, because that's our inside function. Du is 2y dy, and I can move the 2 across, so 1/2 du is y dy. So that this would become the integral of 1/2 du, that's our y dy, and then the square root of y squared plus 2 is u to the 1/2. So now, to integrate that, well, the 1/2 is a constant. Add 1 to the exponent, that's 3/2. Flip the exponent over, 2/3. So, tack on a plus c, so we get, this is 1/3, and then y squared plus 2 to the 3/2 plus c. And so that is going to be our last piece. So plus 1/3 y squared plus 2 to the 3/2 plus c. There we go. All right, good. Whew. I will try to speed up, so don't worry, we'll get there. You have been commissioned to create a work of art on the original polka dot building. In particular, you are to paint 2 non-overlapping circles which are colored blue and red. All right, so we've got some big building here. So we'll draw ourselves a little picture. Here's our building, and we're going to come through and we're going to paint 2 circles. Now let's see, what do we know about these circles? It says that we're required to have the total area of the circles be 169 meters squared, and we're going to be paid 5R plus 12B gold bars. That's how I like to get paid, in gold bars. Where R is the radius of the red circle, and B is the radius of the blue circle. So we've got a blue circle, and we've got a red circle. So maybe, I don't know, something like that. Now, notice that a blue circle, I get paid a lot more. I get nearly twice as many gold bars for my blue circle. So you might be thinking, perfect. We're going to make a polka dot with just 1 dot. Then I'll get a lot of gold bars. And, well, maybe. So the question is, what sizes should you paint the circles in order to maximize your number of gold bars? Now, again, key words, things to look for, maximize. So when we see something like the word maximize, we know optimization. This is an optimization problem. So the hard part about an optimization problem is, let us set up what we're trying to optimize. So we have to figure out what is it we're trying to optimize. Well, gold bars. All right. Well, what is the equation for that? The good news is they gave it to us. And it's what we're trying to optimize is 5R plus 5R plus 12B. Now, at this point, you might say, well, there's nothing hard here. But then you realize, oh, wait a second, I have R and B. Those are 2 different things. When I'm doing optimization, I got to get down to a single variable. So that's always our key. How do we get down to a single variable? Well, we look for other numbers, because oftentimes the numbers are where we figure things out. And here's a number, 169. Well, what is that? Well, it says that the total area has to be 169. Yeah, okay, all right. I do have a typo here. I'm going to quickly correct it. I'm going to put pi, just because it's going to make the computations a lot simpler. 169 pi. All right. So we have a total area that we need. All right. So we say, well, what's the area? Well, we come here. The blue circle has radius b, and the red circle has radius r. So the area is going to be pi b squared plus pi r squared, and that's going to equal 169 pi. So that's the reason I wanted to put the pi's in there, so that we can get rid of the pi's. So we get b squared plus r squared equals 169. So that's what we need. So this is an additional relationship, and now what we can do is we can use this relationship and solve it for either b or for r to get us down to a single variable. It doesn't matter which we solve for. Well, let's solve for b. Like I said, it doesn't matter. So b squared is 169 minus r squared, and so b is the square root of 169 minus r squared. It has to be the positive because we can't paint a circle with negative radius. So now what we have is that the function we're trying to optimize is really 5r plus 12 times the square root of 169 minus r squared. And so I'm going to write this as my function of r. So my function of r looks like this. And I've now finished the hardest part of the optimization problem. I figured out what's the function I need to be using. From here, the rest of it becomes look for critical points and, if needed, classify them. So the way we look for critical points is we take a derivative. So we look at f prime of r. So that's going to be 5 plus 12. Now here, it might be useful to rewrite this function. This is 5r plus 12, 169 minus r squared to the 1/2. So when we take the derivative, the 1/2 comes down. It becomes 169 minus r squared to the minus 1/2. And don't forget to multiply by the derivative of the inside of negative 2r. So here's our function, our derivative of our function. Well, the 2 and the 2 cancel there. So we end up with 5 minus 12r upstairs and the square root of 169 minus r squared downstairs. And we're going to set this equal to 0. Now from here, it's a matter of just patiently working this through and solving. So let's patiently work through and solve. There's not too much to do. There's just 2 terms. And oftentimes when you have 2 terms, you can say, well, let's set them equal to each other. So when you have 2 terms, if you say, let's set both sides equal to each other, the reason we like to do that is that we can do things such as what we call cross-multiplying. When you have 3 terms, oftentimes what you do is say, let me look for factoring. So 5 equals 12r over the square root of 169 minus r squared. I'll cross-multiply, get rid of my denominator. 5 square root of 169 minus r squared is equal to 12 times r. And from here, let's square both sides. Because the safest and surest way to get rid of a square root is to square things. So we get that 25 times 169 minus r squared, there's no square root left, is equal to 144 r squared. And at this point, you probably are getting a little bit nervous and like, am I going to have to multiply 25 by 169? And the answer is you don't have to. Just write it as 25 times 169. Like, okay, that's not so bad. Less nervous. You don't always have to multiply the numbers out. Something nice might happen. If we add 25r squared to both sides, we get 25 times 169 is equal to 169 times r squared. Now what can you do? The 169s cancel. So sometimes if you have unpleasant numbers, it's to your advantage to say, let me hold off for a second. Maybe something nice will happen. It happened here. So we get r squared equals 25. What does that tell us about r? R squared equals 25 tells us r should be 5. Because you take the square root of 25. Now, suppose we know that r equals 5. Well, what about b? So if you take r equals 5 and plug it into your relationship for b, we'll get that. Do a little bit of side work here. B equals the square root of 169 minus 25. Or b equals the square root of 144, which means that we get that b should be 12. So it actually is to our advantage to not put all the money, into that huge blue circle. Even though blue circles are worth more, there's a little bit of a trade-off. And so yes, we'll have a much bigger bluer circle, but having a little red circle increases our profit. Now, let's, for the sake of just in case we run into something, suppose we were asked to show that this answer is indeed a maximum. Because sometimes we do this on optimization problems. Show that your answer is a maximum. Well, how do you show something's a maximum? Well, what you do is you do a test. And I recommend the first derivative test because you've already computed the first derivative and it's right there. And you say, all right, how does the first derivative test work? Well, you know your answer is at 5 and you say, okay, well, where does our interval go from? Well, we have to paint a circle. So we know that we have to be between, the smallest circle I could paint is 0. The biggest circle would be if I just painted a single circle, so 13. So I'm between 0 and 13. So what I want to do is I just want to say, okay, between 0 and 13, I think 5 is the answer. So I just check on either side of 5. And I say to myself, okay, between 0 and 5, what's a convenient number? 1 is a convenient number. So I have 5 minus 12 over the square root of 168. Well, which is bigger, 12 or square root of 168? Yeah, the square root of 168 is actually bigger. So this is actually not a very large number. It's less than 1. So that tells me that in here, f prime is positive. So I'm increasing. How about between 5 and 10? Well, wait, why did I write 10? This should be 13. I'm sorry. Between 5 and 13. Well, just pick a number like 5. Why not? No, 5 you can't pick. That's going to give you 0. That's why not. Okay, now you know. Okay, pick a number like 12. Right? We can do 12. So this would be 12 times 12, it's 144. Downstairs you get 5, because it would be 169 minus 144. Sorry, yeah, 169 minus 144, 25, that would be 5. So you get 144 over 5. That's a huge number, which says, hey, your derivative is negative. You don't need much more than this. But now we see, lo and behold, our profit is going up, our profit is going down. So yes, this is a max. So be ready to be able to justify min or max. All right. Find the tangent line to the curve e to the power xy minus 4 plus sine of x minus 1 plus y equals 5 at the point 1 comma 4. And then it says that given that 0.99 comma b is also a point on the curve, estimate the value for b. So there's two things going on here. So let's talk about the first sentence, because really there's like two actions. There's the first sentence, which is find the tangent line. There's the second sentence, which is about estimation. So let's talk about the first one. There's a clue here, which is this function here. If you look at this function, notice how you do not have it as y as a function of x, but rather you have some equation written down that involves both x and y. So when you see in the equation that you cannot have y as a function of x, that tells you that the tool you should be thinking about is implicit differentiation, because I don't have y as a function of x. So if you have any crazy equation that says, oh, here's this equation, and you cannot easily solve for y, you're like, oh, this is implicit. So you want to be able to recognize, just like, oh, I see there's this formula, no chance to solve for y, think implicit. Now, on a side note, interpret the following statement as you will. It is interesting to say that we didn't test you on implicit differentiation yet. Interpret that as you will. So, how do you handle an implicit differentiation problem? Well, the key here is, even though we cannot solve for y as a function of x, and the reason I say you can't solve for y as a function of x, see how y shows up in two places? And you say, well, if I bring this y down, out of the exponent, I'm going to trap this y inside of a log. So there's no way I can get a single y, because once I free one, I'm trapping the other. So the way to do this is you're on the exam, and you think to yourself, what I'm going to do, and I know this is a speech bubble, this should have been a thought bubble, is I'm going to think of, every time I see a y, I'm really going to think that y is a function of x. And so that's the key. And once you remember that, implicit differentiation is like super, super easy. How does it work? Well, you have exy minus 4 plus sine of x minus 1 plus y equals 5. And the procedure is take the derivative of both sides with respect to x. The only thing is, remember that even though you didn't write it down, whenever you think of y, you're going to think of y as a function of x. So we take our derivative. So e to something, well, it's always e to that something times the derivative of that something. So I take the derivative of x times y minus 4. So derivative of x is 1 times y. then I have plus x times the derivative of y, which we write y prime. Because I remember that y depends on x, so I have to do something whenever I see a derivative of y. The minus 4, well, that's 0. Because that's a constant. The derivative of sine of x minus 1, derivative of sine is cosine. So cosine x minus 1. And I can even times it by the derivative of the inside, which is 1. The derivative of y is y prime. And then the derivative of 5 is 0. So that's the derivative of both sides with respect to x. Now, at this stage, we're after a tangent line, which means I need to find y prime at a particular location, 1, 4. So if I need y prime at a particular location, what I say is, okay, I need to solve for dy dx at 1, 4. So there's two choices. One is take what you have right now and solve for y prime in terms of equations involving x and y. The other is plug in. There's two things that have to happen. I want to be clear. You need to solve for y prime, and the other thing is you need to evaluate. But the thing is, when I put it here, it looks like it matters what order you do it in. The answer is you can do it in either order. So you can either solve for y prime first and then evaluate, or you can evaluate and then solve for y prime. Now, between those two, you really should do it in this order. The evaluation should come first. And as a general rule of thumb, the sooner you can evaluate, the better off you are. And we want to be better off. That's our goal in life. All right. So we plug in x equals 1, y equals 4. So we're going to get e to the 4 minus 4 times 4 plus 1 times y prime plus cosine 1 minus 1 plus y prime. Because I don't know what y prime is. That's what I'm solving for. And if we do this, we say, hey, lots of nice things are going to happen here. E to the 0 is 1, which is great. So we really have 4 plus y prime plus 1 plus y prime equals 0. Or 2y prime equals negative 5, or y prime is equal to negative 5 halves. So what this is this is our slope of our tangent line. And now that you have the slope of the tangent line, and you already have the point. See, that's the nice thing, is the point's given to you, so you don't have to find the point. You put it together. So you can say, for example, y minus the y coordinate is equal to the slope x minus the x coordinate. And that's perfectly fine to leave your answer in that form. Or you could also say that y equals, and I'll write it in this way for what's coming in part 2, y equals 4 minus 5 halves x minus 1. Now we get to the second sentence. So we just did the first sentence. Because really, there's two pieces going on here. So the second sentence, we're told that 0.99 comma b is also a point in the curve. Now, notice something about 0.99b versus 1 comma 4. Well, 0.99 is very close to 1. That's not a coincidence. So what we're saying here is that I have a point nearby that's also on the curve. And I want to sort of get an idea of where should b be, what should the value of b look like. There's one key phrase here that I really want you to focus on, that when you see it, you're saying, okay, that's what I'm going to do. And that's this word estimate. When you see the word estimate, there were two types of estimation that we talked about in this class. Now, the last kind was Riemann sums. Riemann sums we talked about as an estimate for a definite integral, but we're not testing you on Riemann sums on the final. So there's another kind of estimation, which is use your tangent lines to approximate a function. So if you see a word called estimate or anything like that, approximate, probably approximate is the better pronunciation, what that really is a signal to you is it says use the tangent line. The tangent line contains information. So our idea is to say, well, look, this is terrible. I don't want to use it. But locally, whatever this curve is, the curve looks like the tangent line. So what we'll do is we're going to plug in 0.99 into our tangent line. So we can say that our b is approximately, because really we're on approximation of 4 minus 5/2 times 0.99 minus 1. Well, 0.99 minus 1, we could leave our answer like this, but for some reason I'm being greedy and I'm going to try to push this through. 0.99 minus 1, that's minus 0.01. Minus makes plus. And 5/2 is 2.5. And if you multiply that together, you'll get 4 plus 0.025. So this is really 2.5 times 0.01. So we get that b should be approximately 4.025. Now, that is not what b is. It's just an estimate for what b should be. So oftentimes this is a way that you can say, well, maybe I don't know the exact value, but I can perturb a little bit. Okay. We will need to go a little faster because we are running time. I apologize. I'm probably going to go a little bit over. But we're learning good stuff. Find the area between the curves x equals y squared minus 1 and y equals 1/2 x minus 1. Okay, so let's think about these curves. X equals y squared minus 1 sounds like a parabola because it's a parabola. The only difference is we swap the roles of x and y. So instead of a parabola opening up or down, it's a parabola that opens left or right. And in particular, it's this parabola where we put 1 over here at the very far left end. Sorry, negative 1. Y equals 1/2 x minus 1. Now that's a little bit easier to figure out. So that will do the following. It has a intercept at negative 1. Now if you come here and say, where does this parabola cross through the y-axis? So if you set x equals 0, get y squared minus 1 equals 0, it actually crosses at positive 1 and at negative 1. And this line hits at negative 1, then it just has a slope of 1/2. So here's this curve, y equals 1/2 x minus 1. So we are looking for the area between the curves, which means it's this piece right here. So that's the area that we're after. Well, we know how to find area between curves. Now, we can choose to integrate in one of two directions, because we've talked about integrating with respect to x, but we also talked about integrating with respect to y. When we talk about integrating with respect to x, we think about small, thin, vertical slices. Now, the problem if we integrate with respect to x is you'll see that there's this transition in behavior for what's the lower curve. Whenever there's a transition, that means you have to break it up into multiple integrals, and that sounds like more work. Our goal is to do less work. So we check the other direction. When we integrate with respect to y, that's thinking about slicing things up into small little horizontal strips, and you'll notice that it's always consistently the same curve on the left and the right-hand side. In particular, on the left-hand side, it's the curve y squared minus 1. On the right-hand side, well, I don't want to have it as y equals, I want to have it as x equals. So if I add 1 and multiply both sides by 2, I would get that x equals 2y plus 2. Now, the only thing I have to do before I write down the integral is I have to figure out where do these intersect. So when you need to find an intersection point, you set the curves equal to each other. Y squared minus 1 is equal to 2y plus 2. Move everything over to one side. Y squared minus 2y minus 3 equals 0. And hopefully this factors. Well, not hopefully. We know 100% it has to. You're like, how? You screwed up problem 1. I no longer trust that you know that it has to factor, Steve. Well, we know it has to factor because we know where these cross. We already said they cross at -1. So that says that -1 has to be a root, because anywhere where they cross is a root. So it's going to be y plus 1, and then the other one has to be y minus 3, which means that my picture is not very accurate, because that's supposed to be 3. It does not look like that's 3 away. Well, that's the danger of drawing your own picture, but that's all right. Even a bad picture can help you get good insight into what's going on. So the area is going to be the integral where you start to where you stop. That's your bounds. Start at -1, end at +3. Your right minus your left. Or you can think of it as high value minus low value. And the high values tend to be towards the positive infinity. The low values tend to be towards negative infinity. So the high value is 2y plus 2 minus, low value is y squared minus 1 dy. So from here, not much happens after this point. So this is minus y squared plus 2y plus 3 dy. So this becomes minus 1/3 y cubed plus y squared plus 3y. And you evaluate from -1 to +3. So when you plug in +3, you get -1/3 times 3 cubed, which becomes -9, plus 3 squared, which is 9, plus 3 times 3, which is 9. Ooh, lots of 9s. Subtract. Plug in -1. -1 cubed is a -1, so you get plus 1/3. And then you get y squared. -1 squared makes that a plus 1. And then 3y, that's a minus 3. The 9's cancel. Minus, so what do we have? We have 9 minus 1 plus 3. That makes this 11 minus 1/3, which is 32/3. Okay. So it's the setup is the hard part. In fact, I think that's a very common thing, is that a lot of people come in and say, I know how to do the computation. How do I get the setup? So it's a good idea to make sure you can do the setup. All right. Number 13. Find all inflection points of f of x equals 2x squared minus 2x minus 3 e to the 2x, and determine when the function is concave up and concave down. So key word here, inflection points, and also words like concave up, concave down. When we see that, what are we looking for? Second derivative. So this is all about the second derivative. And in particular, what does the second derivative say? Well, it's if the second derivative is positive, you're concave up. If the second derivative is negative, you're concave down. So that's the second derivative. It tells you information about concavity. Inflection point. Inflection point is where second derivative changes sign. So when you're looking for an inflection point, you're saying, when does my second derivative go from negative to positive, or vice versa? So second derivative changes sign. So this problem, well, the first part is just saying, all right, you got to take two derivatives. And so here, we just basically have to be patient. There's no big surprise here. So here's our original function. And I'll take the derivative, 4x minus 2 e to the 3x plus 2x squared minus 2x minus 3 times 2 e to the 2x. All right, so I'm just taking the derivative of the first times the second, except somehow I wrote a 3. Should have been a 2. I want to be careful because I don't want to mess up what comes next. Now, well, let's go ahead and simplify by putting it all together. So what do we have? Well, we'd have 2 times 2x squared, that's 4x squared. Then here we have minus 4x, and there's a plus 4x, which is 0. That's good. Then we have minus 6, minus 2 is minus 8, e to the 2x. So that's our, so this is f. Here is f prime. So now f double prime. So product rule. Go to the first, 8x, then e to the 2x, plus 4x squared minus 8, times 2e to the 2x. And again, let's pull out. What do we have? We have, well, actually it's not so bad here. 4x squared minus 8x minus, oh, whoop, don't forget the 2. It's 8x squared minus plus 8x minus 16. There we go. E to the 2x. Sorry about that. I'm trying to go fast. And when you go fast, you make mistakes. Let this be a lesson. Use your time well. And if you use your time, you can do quite a lot. You got 2 hours. That's a lot of time. How much is 2 hours? That's about how long it's been since we started. I know it feels like it's been 20 hours, but no, it's just been 2. All right. Well, now the nice thing is this is never undefined. All our pieces are nice. Is it ever 0? Well, we should probably factor. We hope it factors. And in this case, it does. It factors as x plus 2, x minus 1. So that says draw a line and mark your places where your second derivative could be 0. In our case, second derivative could be 0 at -2 or at +1. And now you just want to test each piece. You say, okay, well, 0 is a good candidate. Plug in 0. The e to the 2x is always positive, and 8 is always 8. So you get 2 times -1, which says that your second derivative is negative. Now plug in some other numbers, say like 5. Again, it's these terms with the x that determines what goes on. You get 7 times 4, that's positive. So it's positive above 1. Plug in -5, you get -3, -6. But it's 2 negatives, and so you're back to positive again. So our conclusion is we are going to be concave up for the following. Well, where is our derivative positive? So we can say for x less than or equal to -2 and x greater than or greater than or equal to 1. Again, don't worry about the endpoints. It's just the in-betweens. We want to make sure you get those. Concave down, where does that happen? Well, that happens between where our second derivative is negative, -2, less than or equal to x, less than or equal to 1. Inflection points, well, where do we change our signs? We're looking for our sign changes. -2, we change from positive to negative, and then 1, negative to positive. So they're both inflection points. Now, just because your second derivative is 0 at a point does not automatically make it an inflection point. You have to change sign. Yes?
Are we allowed to write interval notation?
Are you allowed to write interval notation? Absolutely. We are adaptable. Any answer that is a commonly accepted notation, including interval notation or something like this, we will accept both of them. We will accept both of them. All right. Number 14. A new chemical composite has been discovered, which has similar properties to radioactive decay, and that over time the composite changes to a different material. However, the rate, this is another typo, sorry about that. The rate in which it changes depends both on how much material is currently present as well as how much time has passed. Namely, we have dy dt equals -5y over 1 plus t squared. Given that at time t equals 0, there are y of 0 equals 6 units of the composite, determine how much of the composite there is at any time t. Well, that's a lot of words to get down to just like I have an equation and I have some initial conditions. And this is an equation that we look at and say, aha, this is a separable differential equation type problem because it involves both the derivative and the original function mixed together into one equation. So this is the one that, again, we'll talk more about in the next few days. But given that we've already talked a little bit about it, we should understand the process pretty well. So from here, what's the process? Well, you're going to go through and you're going to do our separate. So I can say dy over y is equal to -5 dt over 1 plus t squared. Okay, so in this case, it's very easy to separate. It's just sitting there, ready for us to pluck it. We integrate dy over y, natural log y, equals, integral of negative 5 dt over 1 plus t squared. Well, negative 5 is a constant, and then once you have that 1 over 1 plus t squared, that's going to give us arctangent of t. So after we did our separation, we then did our integration. And of course, we need to have a plus c. Now we can solve for c now, or we can solve for c later. Since we did the earlier one, we solved for c now, let me show you what would happen if you solve for c later. Now a lot of times you end up with something with a log. So if we raise both sides, use exponential, we get y equals e to the minus 5 arctangent of t plus c. But this is e to the minus 5 arctangent of t times e to the c, because that addition in the exponent becomes multiplication. And here's a cool fact. If I have e to a constant, this is just a constant. It's a weird looking name for it, so I'm going to replace e to the c. I can say, well, really it says y is some constant e to the minus 5 arctangent of t. Now, so that's our solve for y first, and remember we still have to plug in our initial conditions. We get that 6, because remember y of 0 equals 6, so 6 equals d e to the minus 5 arctangent of 0. Well, arctangent of 0 is 0. And e to the 0 is 1. So that just tells us that d is 6. And therefore, our final answer is that at any given time t, we get y equals 6 e to the minus 5 arctangent of t. And that is how much there is at any given time t. And if you're thinking, that seems pretty quick to do these types of problems, the answer is yes. They should be quick. This is something that hopefully should not be very laborious for you, and you should be able to work through them in just a few moments. All right. So, given that x equals negative 1/4 is a critical point of f of x equals e to the bx over 3 plus 16x squared, determine the value of b and classify all critical points of f of x. Well, if it's a critical point, that tells us something. This function, first off, is not undefined, so it's a really nice function. So critical point, it's probably sending us a signal. It's saying, oh, hey, f prime of negative 1/4, that's 0. So that's the information that we're being told, that when we plug in negative 1/4, we get 0. So we say, okay, so let's look at f of x, and let's see what happens when we plug in negative 1/4. So I'm going to use the quotient rule here, and yes, I know technically the quotient rule has been removed, but we're practicing here. It's okay if we use tools that may not necessarily be on the exam. We're trying to do the concepts. We're working on our other concepts. So we're going to take the bottom times the derivative of the top minus the top times the derivative of the bottom. All that divided by the bottom part squared. And you can do a couple of things. You can pull out your e to the bx, and then if you pull that out, what are you left with? Well, you're left with 3 plus 16x squared times b minus 32x. Then you're going to divide that by 3 plus 16x squared squared. We plug in our negative 1/4. So we know that f prime of negative 1/4 equals 0. So we plug in negative 1/4, we get e to the minus b over 4. That's the p part there. In the denominator, 1/4 squared, and same as negative 1/4 squared, is 1/16. So it really becomes 4 squared. Again, negative 1/4 squared is going to be 1/16 times 16, so that's going to become 4 times b. And then 32 times negative 1/4, well, that's going to be negative 8. Don't forget that there's another minus there already, so that becomes plus 8. And we say, well, the 4 squared down there can't be 0. The e negative b over 4 can't be 0, so that tells us 4b plus 8 has to be 0. So b has to equal negative 2. So that's the first thing. We've now determined the value of B. But then it says, you've got to classify all the critical points. So we say, well, okay, let's figure out what our critical points are. Let's go back in now and plug in what we know for B. And we can plug it in. Oops, that says F. That should be an F prime. I apologize for that. So we plug it in. So we get that F prime of x is e to the negative 2x times negative 2 times 3 plus 16x squared minus 32x over 3 plus 16x squared squared. And where do we want to put our energy? We want to put our energy up here into this part. So let's focus on that. Negative 2 times 3 plus 16x squared minus 32x. If we expand this out, we get minus 32x squared, and then we get minus 32x, and then we get minus 6. Oh, it's very minusy here. Well, these things happen. Let's go ahead and pull out a minus 2. So we get 16x squared, and then we get plus 16x plus 3. Yes? I think that's it. That looks right to me. Now at this point you're probably like, oh, we're going to have to factor that, aren't we? But we have some help. What do we know? We know a 0 because we were told a 0. So we know this has to factor. In fact, it has to factor as x minus minus a fourth, which is x plus a fourth. And once we know that that's a factor, that says, okay, what's the other part have to be? Well, to get from x to 16x squared, there has to be a 16x there. To get from 1/4 to 3, well, that means that there has to be a plus, what would that be? 12. So that's our other factor. Now actually what you would probably do is pull a 4 out of here, move a 4 into there. So negative 2 times 4x plus 1 times 4x plus 3. So where are our critical points at? Well, there's 2 of them. There's one at negative 1/4, and there's another one at negative 3/4, because that's when we get our zeros. So coming back over, updating our f prime of x. We got a little bit of space down here. We can do that. So we get minus 2 e to the minus 2x, 4x plus 1, 4x plus 3, all divided by 3 plus 16x squared squared. So we just throw in some points and test. Suppose we test something above negative 1/4. Any convenient numbers there? 0, 1. Plug in 0. We get negative, positive, positive, positive. Downstairs always positive. So that says that our function here is negative. So it's decreasing. So f prime negative. Between negative 1/4 and negative 3/4. Negative 1/2. So we get a negative, a positive, negative 2 plus 1. Now that's negative. Negative 2 plus 3 is positive. And then downstairs is positive. So we're ending up with 2 negatives. So that net result is positive. Sorry, not second derivative, first derivative. That's a very big prime. All right, now negative a million. Doesn't have to be negative. Anything below negative 3/4. Negative 1 can do it. Negative, positive, negative, negative. So we're now back to negative. So we were asked to classify. We see that we are going down, then we're going up, and then we're going down. So we have that negative 1/4 is a local max, and that negative 3/4 is a local min. So there's our classification. Which brings us to our last problem. Whew. All right. And thank you for staying to the end. We'll finish on a high note, maybe. So you have a large helium balloon. And so we have, here's our ground. and there's this balloon. And it's attached to the ground. This cable here, this is 50 feet long. Now, what happens? Well, while this balloon is in the air, all of a sudden there's a strong gust of wind. It's blowing here, and the result is that it starts to move sideways. Now, it's not going to move exactly horizontal, so it's really what's going to happen is initially it was up here, and it's going to move down and more or less fall along the edge of the circle. So that's what happens when you have a strong wind blowing against a balloon tied to the ground. Now, what are we told? The location of the balloon is directly overhead from a point 30 feet away from which it is tethered. So right now, we're told that this distance is 30 feet. And the distance from where it's being tethered is increasing at a rate of 2 feet per minute. In other words, this is increasing at 2 feet per minute. Now the question is determine the rate at which the distance from the balloon to the ground is changing. So in other words, how is just changing? What is this rate in terms of feet per minute? So that's our goal, is to figure out how quickly it's dropping towards the ground. Well, all right, let's see if we can figure this out. Now, we know the length here is 50. This length down below is 30. Can we figure out the current height of the balloon? Yeah, someone has said 3, 4, 5, right? You might be, why do you keep doing the same 3, 4, 5 triangle over and over again? Aren't there not other triangles in the world? And the answer is, we're trying to give you examples that are computationally easy. We really don't care about the numbers, we care about the processes. So you will see 3, 4, 5 triangles show up a lot in calculus. All right, so we have our 3, 4, 5 triangle ready to go. Life is good. We need to label things. So let's just strip away our picture here, and we label things. Anything that can vary, we attach a variable name. So x and y, those two sides can vary. Anything which doesn't vary, just write in what the value is. So 50. The hypotenuse can't vary. And now we say to ourselves, okay, what do we do? Well, we look for a relationship, and a big one, Pythagorean theorem. X squared plus y squared equals 50 squared. So Pythagorean theorem, similar triangles, those are very common in related rates. Other things are things like shapes, maybe 2-dimensional or 3-dimensional shapes, a common thing. At this point, this is the relationship. Now you just have to bring in the rates. So we take derivatives to do that. 2x dx dt plus 2y dy dt equals 0. The 2's can be divided out, go away. And then you plug in what you know. You know x is 30. Dx dt is 2. By the way, is dx dt positive 2 or negative 2? Positive 2, because it's an increasing. It's getting further away, so the length is getting larger. Plus y, that's 40, and then times by dy dt, which we don't know, but we will soon. So that's equal to 0. So 40 dy dt is equal to negative 60, or dy dt is negative 60 over 40. The zeros cancel. And negative 6 over 4 is negative 3 over 2. So we are dropping, and we can use this phrase, dropping at 3/2 feet per minute. And when we're about the sign is embedded into the word dropping. So it is dropping down at 3/2 feet per minute. That's what's going on. That was our last problem. Thank you for being very patient. I hope this helps. I do hope you spend more time reviewing and studying. The more problems you do, the better off you will be.